In the last video, we looked at exponential growth and exponential decay, and we said that we could model them by the equation A equals P e to the RT. There's lots of versions of this. I actually said that a lot of times I prefer to write a K there because that's a standard growth or decay constant. It doesn't matter. The equations are standard as long as you understand what they mean. We looked at half-life, but I wanted to make this video going over some more advanced problems because once we understand what we're doing, then the question becomes, how difficult can I make the problem and still solve it using my understanding of half-life and exponential equations? So as an example, suppose I say this. The half-life of uranium-37 is 400 years. When will I have, we'll go with 30% of my starting value? Right away, I know it's exponential growth or decay, in this case clearly decay, so I get my equation A equals P e to the KT. And from the last video, we know how this works. I need to find K. The problem is I need an A, a P, and a T that are related. In the last video, we had a starting value, P, that we would plug in, but I'm not given that here. So what do I do? And there's a trick here, because of the way half-life works. Pick a starting value. For the sake of argument, I'm going to let P equal 100. And say I start with 100 grams. Then I get A equals 100 e to the KT. And now, if it is okay for me to let P equal 100, then see what happens. Plug in a T and an A that are related. We said the trick last time, use my half-life. When time is 400, so 100 e to the 400k, I get half of what I started with. So this is 50. Now I solve for k. I divide the 100. 50 divided by 100 is a half, equals e to the 400k. I take the ln of both sides. ln of a half equals 400k. I divide the 400. K is ln of a half over 400. Assuming it's okay for me to let P be 100. But suppose I started with a different value. Suppose I started with 300 grams. Then I have A equals 300 e to the KT. I do the same thing. I plug in the T and the A that are related by half-life. So when time is equal to 400, my half-life, I have half of what I started with, that's 150. But then to solve for k, I divide the 300. 150 divided by 300 is a half, equals e to the 400k. I take the ln of both sides. ln of a half is 400k. I divide the 400, and I get ln of a half over 400. Well, that's the exact same k I got there. And all that really means is, while we can be given the starting value, when we're talking about half-life, it doesn't actually matter if we have a starting value or not. In fact, the growth, or in this case, decay rate for half-life is always the same. It's ln of a half divided by the half-life. In this case, 400. If you look at the last video, I think we had a half-life of 200 years, and the decay rate we got was ln of a half divided by 200, because it's always the same. So even if I'm not given a starting value, and if I'm not given the growth or decay rate, I can still find it because there's a standard algebraic trick that gets it for me. Now, if I plug it into my calculator, let's see, ln 0.5 divided by 400, negative 0.0017. So k is negative 0.0017. We said last time, my decay rate should definitely be negative. That's what makes it a decay rate. So now I rewrite the equation. A equals P e to the negative 0.0017t. But I still don't have a starting value in there. And now I want to know when I have 30% of what I started with. But I don't know what I started with. But based off of this, it clearly doesn't matter what I started with if all I care about is the percentage. So just make it up. You can use any number you want. Since we're talking about percents, I'm going to say I started with 100. Then 30% of 100 is just 30. So I want to know when I have 30 grams left. Now I solve the problem. Divide the 100. 30 divided by 100 is 0.3 equals e to the negative 0.0017t. And do the exact same algebra as before. ln both sides. You get ln of 0.3 equals negative 0.0017t. Divide this. We get t is equal to ln of 0.3 divided by negative 0.0017. And we said last time, yes, this is negative here, but this is the ln of something less than 1, which means it's going to be negative as well. Then I'm going to have a negative divided by a negative, which will be positive, which is what I want. So ln of 0.3 divided by negative 0.0017, and I get 708.2. And we did all this work, and now we're just kind of assuming that that's correct. One way we can check it is to do what we also did last video, use an understanding of half-life to approximate the solution. So just really quickly, to make sure all of our math is sound, when time is 0, suppose I have 100% of whatever I start with. Half-life is 400 years, so when time is equal to 400, I'll have half of this, which is 50%. 400 years later, when time is 800, I'll have half of this, which is 25%. I want to know when I have 30% left, which clearly has to be in here. And if you think about it, 30 is closer to 25 than 50, so my answer should be closer to 800 than 400. And I got 708.2, which means all of my math and my setting up just a random starting value and all that seems to work completely fine and give me an answer that makes sense in the context of the problem. And the reason I do this is, can you be given a problem where you're told the growth or decay rate, population growth, half-life, decay, whatever, and then you really just plug in and hit enter on your calculator? Yes. And all things being equal, you're really not going to do that much in this class. Generally, you won't be given the growth or decay rate, but the algebraic trick to find it's pretty straightforward. Plug in the initial value, plug in a time and an amount that you're given, algebraically solve using the ln to get the growth or decay rate, rewrite the equation with that rate in there, and then maybe solve another problem. But you can actually go a step further, not be given the growth or decay rate, and not be given the starting value, and still solve the problems using the algebra that we know. So just be aware, there's kind of a wide variety of questions you can be asked. As long as you understand there's a basic starting equation for exponential growth and decay, the rest of it can be worked out algebraically using the tricks we know. If you would like more examples of this worked out, just let me know as usual, and I'll make more videos going through more examples or homework problems.